I said this earlier, arguably DNA binding to proteins, or I should say DNA binding proteins, proteins that will bind to DNA such as transcription factors, have maybe a very strong need for specificity in order to make sure you turn on the right genes when you want them and you don't turn on genes when you don't want to. In reality, while transcription factors do have a very high affinity for their target sites, and they also have very low affinity for off-target stuff, there's so many off-target sites, and we're summing up that bottom piece of our specificity calculation, that in fact specificity is still around about 0.1, just because there are so many off-targets. So let's do this example problem. So take a minute and work through this one. A single molecule microscopy experiment is performed on a slide. It has 1,000 molecules each of green, red, cyan, and yellow fluorescent proteins. Okay. The experiment measures the number of antibodies that bind to each of them. You find that 900 of your molecules, of your GFP molecules get found, 10 of your red ones get found, 1 of your cyan ones get found, and 3 molecules of yellow fluorescent protein are bound up at, we have a 1 nanomolar concentration of our antibody. Okay? So first of all, stop and think, which ones are our receptors? What is our ligand in this situation, right? Then you're calculating 2 things: the specificity of the antibody for GFP, and case of D of the GFP antibody interaction. I will say this, we're just talking about number of molecules, we're not in molar. Doesn't really matter, we know how to get between number of molecules and molar. We can use Avogadro's number, but since we're taking a ratio and everything's going to drop out, I would leave things in number of molecules to make the numbers easier. If you want to multiply everything through by 10 to the 23rd, or go for it, or divide by 10 to the 23rd. But where is